Welcome to Spaceverse, your portal to cosmic adventures. In the vast and mysterious cosmos, few discoveries capture both scientific curiosity and public imagination, quite like the search for alien life. And at the center of one of the most heated debates in modern astronomy lies a single, curious molecule, phosphine. For years, this molecule has intrigued scientists because, on Earth, phosphine is primarily produced by life, specifically by microbes that thrive in oxygen-free environments. So when astronomers thought they'd found it in the atmosphere of Venus, the implications were staggering. Could there be life in the planet's scorching, sulfuric clouds? But now, the James Webb Space Telescope has detected phosphine somewhere very different, in the cold atmosphere of a brown dwarf called Wolf 1130c. And this new discovery may hold the key to solving the mystery of phosphine and what it truly means when we find it beyond Earth. Wolf 1130c is no ordinary object. It's a brown dwarf, a celestial body that sits in the strange gray area between a planet and a star. Too massive to be a planet, yet too small to ignite hydrogen fusion like a true star. Brown dwarfs are often called failed stars, but their atmospheres can teach us a great deal about planetary chemistry and possibly the origins of life's building blocks. What makes Wolf 1130c fascinating is that JWST detected phosphine in its atmosphere at an abundance of about 0.1 parts per million. This might sound small, but it's right in line with what models predict for the atmospheres of gas giants and brown dwarfs. Interestingly, Jupiter and Saturn contained roughly the same amount. At first glance, this might not seem groundbreaking. Phosphine on a gas giant or brown dwarf is, after all, expected. But here's where the puzzle begins. Many brown dwarfs that should have phosphine don't. JWST has looked at several others, and for reasons we don't yet understand, phosphine simply isn't there, or is so scarce that it's undetectable. So, what makes Wolf 1130c different? To answer that, we need to understand how phosphine forms. Phosphine, one atom of phosphorus and 3 atoms of hydrogen, is a fragile molecule. It doesn't last long in most atmospheres because chemical reactions tend to tear it apart. On Jupiter and Saturn, phosphine is formed deep within their hot interiors. There, under immense pressure and heat, phosphorus combines with hydrogen to form the molecule. Powerful convection currents then carry it upward faster than it can be destroyed, allowing it to accumulate in the upper clouds, where telescopes can spot it. This process makes perfect sense for gas giants. But Venus is a very different world. Back in 2020, a team led by Jane Greaves at the University of Cardiff announced something extraordinary. They had detected phosphine in Venus's upper atmosphere using the James Clerk Maxwell Telescope in Hawaii and ALMA in Chile. On Earth, phosphine is mainly associated with biology, found in oxygen-free environments like swamps or produced by microorganisms. So when the team found phosphine on Venus, they made a daring suggestion. Perhaps, just perhaps, something was alive in the planet's thick, toxic clouds. For a moment, the world was captivated. Was there life on Venus after all? But the celebration didn't last long. Other scientists soon challenged the results, claiming that the analysis was flawed or that the supposed phosphine signal was actually noise or something else entirely. Subsequent attempts to replicate the finding produced mixed results. Some saw traces of phosphine, others didn't. The debate quickly became one of the most controversial in recent astronomical history. Jane Greaves' team has since stood by their findings, but the community remains divided. Part of the skepticism comes from basic chemistry. Venus's atmosphere is incredibly harsh, full of sulfuric acid, extreme temperatures, and crushing pressures. It's hard to imagine how fragile phosphine could survive there for long. Yet despite the ongoing debate, phosphine remains on the shortlist of potential biosignatures, molecules that could indicate the presence of life. And that's what makes the new JWST finding so important. By detecting phosphine on a brown dwarf, a world far too cold and lifeless for biology, astronomers are reminded that phosphine doesn't have to mean life. Non-biological or abiotic processes can produce it too. So the real question is, why do some worlds, like Jupiter, Saturn, and now Wolf 1130c, have detectable phosphine, while others don't? To unravel this mystery, we turn back to the Wolf 1130 system itself. It's a triple system made up of a red dwarf star, a white dwarf, and the brown dwarf Wolf 1130c orbiting the pair. Here's where things get interesting. Before the white dwarf became what it is today, it was once a massive star, about 6 to 8 times the mass of our sun. Stars like that don't explode as supernovae. Instead, they expand into red giants, shedding their outer layers and leaving behind a white dwarf, a dense Earth-sized stellar core. In those dying moments, the red giant would have forged phosphorus deep in its interior, one of the elements needed to make phosphine, and then expelled it into space when it lost its outer layers. It's tempting to think that this phosphorus-rich material could have rained down onto Wolf 1130c, seeding it with the ingredients needed to make phosphine. But there's a catch. The white dwarf and red dwarf, Wolf 1130a and Wolf 1130b, orbit so closely that they're tidally locked, constantly showing each other the same face, like an eternal cosmic dance. The white dwarf's gravity even stretches the red dwarf into an egg shape. When the white dwarf's progenitor was shedding its outer layers, those gases likely engulfed the red dwarf, but not the distant brown dwarf, which orbits much farther out. And if the brown dwarf had been coated in phosphorus, we'd expect to see similar phosphorus enrichment on the red dwarf, but we don't. So that explanation doesn't hold up. Another theory looks at the chemical makeup of Wolf 1130c itself. Some models predict that atmospheres with very few heavy elements, or low metallicity, as astronomers call it, favor the production of phosphine. And indeed, Wolf 1130c appears to be metal-poor. Interestingly, so are Jupiter and Saturn, both of which also have phosphine in their clouds. This could explain why phosphine is relatively abundant there. Fewer heavy elements might mean fewer competing molecules that destroy phosphine, allowing it to survive longer. It also makes the phosphine spectral signal easier to detect because there's less interference. However, this theory still has a flaw. Other brown dwarfs with similarly low metallicities don't show phosphine either. So there must be something else at play, something in our understanding of atmospheric chemistry that's still missing. The authors of the new research, led by Adam Bergesser from the University of California, San Diego, put it bluntly: the inability of models to consistently explain all these sources indicates an incomplete understanding of phosphorus chemistry in low-temperature atmospheres. We therefore caution against the use of phosphine as a biosignature until these discrepancies are resolved. In other words, we still don't fully understand how phosphine forms, behaves, or survives in different planetary environments. That's a big problem for astrobiologists, because if we can't even explain phosphine on brown dwarfs, where we know life doesn't exist, how can we confidently use it as a sign of life on exoplanets? Still, this discovery is a powerful reminder of why astronomy is both thrilling and humbling. Every time we think we've found something definitive, a signal of life, a pattern that explains the universe, the cosmos throws us another curveball. The detection of phosphine on Wolf 1130c doesn't confirm life, but it does confirm something equally profound. Our understanding of planetary chemistry is still evolving. The universe is a complex laboratory, and every new discovery, even one as subtle as a faint trace of phosphine, teaches us more about how worlds form, evolve, and interact. So while it's too early to celebrate the discovery of alien microbes, it's the right time to appreciate what this moment represents. A new step toward refining the tools and knowledge we'll need to recognize life when we truly find it. In the end, phosphine remains a mystery, a molecule that bridges the gap between biology and chemistry, between life and the lifeless. Wolf 1130c's discovery reminds us that not every chemical clue leads to biology, and not every hopeful sign points to life. But every observation, every data point, brings us one step closer to understanding what it really means to be alive in the universe. Because perhaps the real wonder isn't whether phosphine means life, but how the universe keeps challenging us to keep searching for it. The discovery of phosphine on Wolf 1130c shows us that the line between chemistry and life is thinner than we thought, and that the cosmos still guards its secrets carefully. Whether it's Venus's clouds or a distant brown dwarf, every strange signal tells us there's still so much more to learn. And that's it. Thanks for watching, and if you love diving into the mysteries of space, from the chemistry of alien worlds to the hunt for life beyond Earth, make sure to like, subscribe, and join us again here on Space Verse, where curiosity never stops exploring the universe.